Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of mathematical thought, the year 1797 presents a pivotal moment. It witnessed the publication of Joseph Louis Lagrange's theory des fonctions analytiques, a work whose influence reverberates through the landscape of calculus and analysis even today. To fully appreciate its significance, one must first grasp the intellectual milieu from which it emerged and the specific problems it sought to address. Lagrange, a figure of supreme intellectual stature, had already made substantial contributions to mathematics and physics. His work on the calculus of variations, celestial mechanics, and the theory of equations solidified his reputation as one of the foremost scientists of his era. However, a persistent dissatisfaction with the foundations of calculus, particularly the reliance on infinitesimals and the nebulous concept of limits, drove Lagrange to seek a more rigorous and, in his view, more elegant approach. This dissatisfaction was shared, to varying degrees, by other prominent mathematicians of the time, including D'Alembert and Euler. They, too, recognized the conceptual fragility underpinning the calculus of Newton and Leibniz, even as they celebrated its immense practical set. The existing calculus, as practiced, involved concepts that at times felt ad hoc. The reliance on infinitesimals, infinitely small quantities, posed philosophical challenges. Though they proved useful, a rigorous justification eluded mathematicians for generations. Furthermore, the concept of limits, which sought to define calculus operations with greater precision, had, at this time, a certain vagueness. Lagrange's ambition was to establish calculus on a foundation entirely independent of these problematic elements. The theory des fonctions analytiques represents his attempt to achieve this ambitious goal. At the heart of Lagrange's theory lies the concept of representing functions using their Taylor series expansions. He proposed that every analytic function, that is a function expressible as a power series, could be completely characterized by its coefficients. These coefficients, he argued, could be determined solely from the function's derivatives. Lagrange's core insight involved the systematic application of Taylor series to expand functions, express them as a series of terms involving derivatives, thereby create a purely algebraic approach to calculus. Here is the essential framework of the work expressed in modern notation. If we have a function, f of x, we can represent it at a point, a, using its Taylor series. The Taylor series is given by the sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial multiplied by the quantity x minus a to the power of n. Lagrange focused considerably on functions that could be represented by this power series, those functions which we term analytic functions. For analytic functions, Lagrange considered the derivatives to be the fundamental building blocks. The practical significance of this approach was considerable. Differentiation and integration, the two fundamental operations of calculus, could now be recast as algebraic processes. Lagrange demonstrated how to derive rules for finding derivatives and integrals of various functions using only algebraic manipulations. He believed this would allow for a more systematic discovery of the rules and theorems of calculus, reducing the need for geometric intuition or the somewhat opaque notion of limits. Furthermore, Lagrange's method offered a unified way to handle various problems in calculus. For example, problems in maxima and minima could be solved by simply finding the zeros of the first derivative, a purely algebraic task. This approach, at first glance, seemed to sidestep the complexities of the limit concept by emphasizing algebraic manipulation. The immediate impact of the theory des fonctions analytiques was substantial but complex. The book was quickly recognized as a significant intellectual achievement. It offered a fresh perspective on the foundations of calculus, aiming towards logical rigor. It presented a systematic approach to the subject that appealed to mathematicians, seeking a more elegant and consistent treatment. Lagrange's treatise received considerable attention. His ideas were debated, scrutinized, and built up. However, the reception of Lagrange's work was far from universally positive. The very elegance of his approach became a point of contention. While some mathematicians embraced the algebraic purity of his methods, others voiced concerns about the limitations of his focus on analytic functions. The theory struggled to accommodate functions that could not be expressed by a power series, such as many of the commonly encountered functions in physics and engineering. The definition of a derivative as the coefficient of a Taylor series proved problematic for functions that were differentiable but not analytic. Lagrange's approach therefore had gaps. Moreover, the absence of a rigorous treatment of convergence The essential question of whether these Taylor series actually equal the target functions weakened the foundations. Lagrange did not provide a rigorous definition of the limit, nor did he fully address the nuances of infinite series. The theoretical structure, though elegant, had limitations. The treatment of convergence remained somewhat informal. This, in time, became a point of criticism. The theory des fonctions analytiques did not entirely displace existing calculus. It offered an alternative formulation, an approach that was both insightful and, simultaneously, somewhat incomplete. As a consequence, the work sparked a period of intense debate and critical reappraisal of the foundations of calculus. Lagrange's work builds directly from prior mathematical endeavours. The work of Isaac Newton and Gottfried Wilhelm Leibniz created the calculus. However, Lagrange, along with others, sought a more rigorous and systematic foundation. The calculus of variations, developed by Lagrange, provided an analytical framework that influenced later work. Lagrange's earlier work strongly shaped his thinking. The influence of Lagrange's theory on later mathematicians is readily apparent. While Lagrange's specific approach eventually gave way to a more comprehensive understanding based on limits and epsilons and deltas, his emphasis on the use of power series and derivatives laid the groundwork for later developments. Indeed, Bernard Bolzano would later offer a rigorous treatment of the limit concept, contributing greatly to making the foundations of calculus sound. Augustin Louis Cauchy would build upon Lagrange's insights, developing a modern approach to real analysis, which made the underlying concepts rigorous. Cauchy's work, which included precise definitions of concepts like limits and continuity, provided a more complete framework. The theory des fonctions analytiques served as a catalyst, stimulating the development of improved mathematical tools. The work propelled further exploration of fundamental questions. It spurred mathematicians to grapple with the issues of rigor, convergence, and the nature of functions. The book forced mathematicians to confront these issues directly. Lagrange's focus on the derivative and the Taylor series expansions had lasting repercussions. His emphasis on the expansion of functions in terms of their derivatives remains a central theme in analysis. His approach found applications in areas such as differential equations, where the series solution method is a highly important technique. Furthermore, Lagrange's use of algebraic techniques to derive results in calculus anticipated the rise of symbolic computation. The work influenced the development of complex analysis, which expanded the notion of functions to include complex numbers. Cauchy's work, which built upon Lagrange's ideas, work of Karl Weierstrass, who emphasized the importance of rigor, offered insights that stemmed from Lagrange's. Despite its limitations, the theory des fonctions analytiques retains its historical significance. It exemplifies a persistent quest for a mathematically rigorous foundation. Lagrange's work represents a sustained effort to clarify the concepts. It demonstrates a profound commitment to the pursuit of mathematical truth. Lagrange's treatise, ultimately, stands as a testament to the iterative nature of intellectual progress. It was an endeavor to improve the understanding of calculus. It spurred others to address its shortcomings. While its specific approach has receded in favor of more comprehensive theories, its influence, as a source of ideas, persisted. The theory des fonctions analytiques did not arrive out of a vacuum. It reflects the intellectual climate of its time. It was influenced by the work of D'Alembert, Euler, and others. These mathematicians shared a common goal of clarifying the foundations of calculus. Lagrange built upon their insights. He refined their ideas, pushed the boundaries of mathematical rigor. The work, in turn, influenced a subsequent generation of mathematicians, including Cauchy, Weierstrass, and others. These figures built upon Lagrange's foundation and brought about a more complete understanding of the subject. This represents a clear line of influence from Lagrange. Lagrange himself was a product of his time. He was also an innovator. His work reflected the prevailing trends of the Enlightenment period. It also pushed the boundaries of mathematical knowledge. This juxtaposition of old and new resulted in a lasting legacy. In conclusion, Lagrange's theory des fonctions analytiques is far more than a historical artifact. It provides a window into the evolution of mathematical thought. It offers insights into the development of calculus. The work reflects the power of intellectual ambition. It exemplifies the continuous pursuit of mathematical precision. It serves as a reminder that scientific progress is an ongoing process, which involved critical evaluation, refinement, and the constant striving for greater clarity. It remains a cornerstone in the history of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.